welcome. Thanks for your interest in simplicity. I'm going to talk about this today. My main goals are to give you like a high-level overview of what simplicity is, because that might not be clear to everyone. And the second goal is to actually show it to you, like what is a useful simplicity program, small example, and also how it integrates with existing Miniscript that you might know. So let's dive in. Why do we need that stuff? Why should we care, right? And you should verify our coins. You know, Bitcoin script, this is the scripting language that is used for Bitcoin. And you might know of UTXOs, unspent transaction outputs. You might know that in order to spend your Bitcoin, you need to make a script succeed using witness. And if you can do that, if you can provide such a witness and broadcast that, then you can spend it. And if not, then you don't. But there are always bugs, right? It's always a tiny chance that you can introduce a bug. And if you repeat that process, then it's 100% probable that you will have bugs. And we also shouldn't forget about malicious actors, right? Someone who tries to scam you, right? This will happen. That's a question of how can you defend against that and how can you be sure who can spend your coins. With Bitcoin script is unfortunately very hard to do until you can spend your coins. And so it's not the ideal language for Bitcoin. And as you know, Miniscript was developed by Andrew and by Peter for this purpose. Miniscript is a declarative contract kind of language, which can compile to Bitcoin script. So what we do is we hide these ugly details from you and let you concentrate on the spending. Who can spend what? Public key, okay. Time block, okay. And then some ends and ors, some thresholds and whatnot, right? And we hide opcodes from you, we hide the stack from you. And we make sure that we stay in a safe subset of Bitcoin script, so we don't have any op-ed and anything. We stay in a smaller subset of everything that we deem useful, pay to public key hash and so on, multi-sig and so on. And importantly, by doing this, we can reason about who can spend what. We can enumerate everyone who can spend your coins, which is really hard, if not impossible for Bitcoin script. And we can also talk about the fees, how expensive it is to redeem this on blockchain. We can produce the most efficient Bitcoin script for such a policy. And so this is why we need Miniscript. And so where does simplicity fit into all of this? Well, simplicity is an extension of that. We extend Miniscript, and instead of compiling to Bitcoin script as a backend, we can also compile to simplicity. And on the one hand, simplicity is more powerful. So we can do smart contracts, we can do governance stuff, we can do pretty crazy computations within reason, much more than Bitcoin script. But at the same time, we stay verifiable. We have sound theoretical foundations. Simplicity is not based on a C++ implementation, but it's based on theory. And so sound foundations, and this really mirrors the approach of Miniscript. It's basically the better backend, correct backend for Miniscript. So, but okay, that's nice. We want to verify our coins. We want to have the sound backend. What does that look like, right? And it turns out that we need some bare bones type theory, but this will just be one slide, much less than in the tech report. So, what do we have? Is there any pointer or anything? Like a laser pointer?
I don't think we do.
Okay. I just point. I just realized that I look at the slides a lot. Okay, maybe like this, right? So, who of you guys is a programmer? Like, has written any code? Like,
I'll stick them way up. It's okay.
A little bit.
a little bit, right?
Yeah.
and maybe your language has types. If it's not Python, then you know that variables have types, and these types limit the kinds of values that this variable can contain. Like the integer can only be like 1, 2, 3, cannot be ABC, and it's also bounded, right? It's 32-bit, cannot be larger than that. And so simplicity has the same, although much simpler. And so we start with the unit type, and the unit type is just, we call it 1, and it can just be one value, the unit value, which is just the empty tuple. And on its own, it doesn't really do much, doesn't have any information, it's just there. But we use it to construct everything else, like it's the basis of everything else. And then I talked about combinations, right? We can combine the unit type to create something interesting. And we use sums and products. And so the sum type takes two types, A and B, and then it combines them, A plus B, sum of A and B. And what that means is either we have A or we have B. It's like a disjunction, right? So, and the values, we call this the left value and the right value. So either we have left of A, where A is the value of type A, or we have right of B, where B is of type B. Either left or right, but not both at the same time. And I think that's very intuitive if you think about it. One interesting trivia, or nice thing to know, is that the way we represent bits in simplicity is by using a sum of unit and unit. And so left of this empty tuple is a 0, and right of this empty tuple is a 1. And I think you can start to see how we can represent everything using this very simple system, because the second combination is the product. And here with the sum, we have either left or right. With the product, we have both at the same time. It's a pair, A and B. And I think it's easy to see that we can have like lots of pairs of bits, and then we have bytes and whatnot, like large bit strings. And that's all we need. That's it. That's the type theory we need for simplicity. Not so difficult. But on its own, that's just constants, right? Okay, there's values. We need computation, right? We need to take inputs and produce outputs. And so for that, we have terms. And terms are just functions from one type to another type. And if you're a programmer again, you know what a function is, right? We take inputs and produce outputs. Something that might make more sense even is to think of these terms or these functions as circuits, right? Because simplicity consists of circuits basically that take inputs and produce outputs using kind of gates, gate-like structures. And the way we do this is inductively. So we have combinators that enable us to take sub-functions, 0, 1, 2, and then it produces a larger function. And by stacking these gates, like there are gates that produce constants, there are gates like that kind of ends and so on. By doing so, we can create all the circuits we need. Just like the high-level idea. And I actually want to enumerate all the combinators we have, because they're not actually that many. Constants, right? We need to start from somewhere. We need to create our circuits, and if we need to start with something that doesn't take any arguments, right? It's just there. The unit. So the way I illustrated this is as follows. This is a circuit. That's its name. It's, in this case, the unit circuit, the unit term, or the unit combinator. Remember, the combinators are used to create these terms. And this is a circuit that takes type A, a value of type A, and then it produces a value of type 1, which is the unit type. And in the case of the unit combinator, there is no connection between those two. It just produces unit all the time. It just produces the empty tuple as a constant. And by combining this with other combinators, we can produce also, we can add to any constant we want. Any bit, any witness, anything you want. Speaking of witness, so there's a very similar combinator, the witness combinator or the witness circuit. And it takes any input and then produces an output. And again, there is no connection between input and output because this is just ignored. And we just produce a constant output. And the interesting part about the witness combinator is that it's basically the SegWit, the way how we integrate SegWit in simplicity. Because at commitment time, right, when we create the UTXO, we don't show anything. We don't show the content. We don't commit to the content of this witness. But when we redeem the coins, when we execute the script, we input the value of type B that we need. And this is for malleability reasons, right? So simplicity is compatible with SegWit. We have a witness that is separate from the signature from script sig. And it produces a constant. The identity combinator just produces what it gets, right? So we take the input A, we produce the same, quite normal, quite standard. And then the fail operator fails. So it takes anything and produces anything, like doesn't care because it doesn't even reach that because it fails. And that might seem silly, but then we remember that often we want our program to fail, like given certain conditions, and there are kind of if statements in simplicity, we want it to fail, and then we can use this fail operator to realize that. So those are the constants, right? This is how we start making our circuits. Those are already circuits, right? Those are circuits. Those are completely programs. But those, on their own, they don't really do anything. So it's about how we can combine those. That's why they're called combinators. How we can build larger circuits out of these atoms. And one way to do it is the composition, right? And if you're a programmer, maybe you know of chaining, right? Like you chain functions, you apply one function and then you apply a second function onto the output of the first function. And this is the composition combinator. And so the visualization is slightly different. So here in light gray, I have existing circuits, right? So this is this inductive construction. We have some circuits, and then we produce a larger circuit out of these existing circuits. A to B, B to C, okay, we produce a circuit A to C. Easy. And this is like a linear kind of composition. And then we can also do this in parallel, right? So we can connect our input, and then just two circuits, use this input at the same time and produce a pair of B and C, of both of the outputs. And this is the pair combinator. Those are two very natural ways to combine, to chain, so to speak, to compose existing circuits, existing functions, either in sequence or in parallel. Okay. What about sums? So I talked about how we represent bits and sums and so on. And what we can do is we can use the left and right injection to take a circuit from A to B, and then the left injection wraps its output B in left of B, and then the output type is B or C, or B plus C in the previous notation. And we never have any C value, we always have B, but the type is B or C because it's left of B. And the right injection is analogous to that, so we have taken our input A, wrap it to C, and then we wrap it in the right value, right of C, which is B or C. And this way we can produce sums if we need them. What we can also do is we can deconstruct products. So as I showed with the pair, we can create those products, those pairs, and often we only want certain values, right? We have a long pair, we only want to select one value of those and then execute a function on that. And so the take combinator takes the first element of the pair and then applies the function, applies the circuit onto it, uses C, and the drops the first argument, uses the second element, and applies a function to it. Again, very natural. We select what we want to use in the pair, and then we apply a function on it. And the last major piece is branching. So pretty much every programming language has an if statement or something similar. And here, this is called case. And the way it works is as follows. It takes a pair, and the first element encodes which way we want to go. It's a sum. So this is one major way how we use sums. And either this is A or B. If it's A, we go to the upper branch and use this circuit. If it's B, we go the lower branch. Right? And so the first argument, either for this or for this, and using the sum, we know left goes up, right goes down. And the C, which is the second element of this larger pair, is always an argument for these circuits. And then circuit produces D, output D. And this is enough to realize arbitrary computation. But something I also want to mention, even though this doesn't, the reason why they exist, why these combinations exist, it's kind of out of scope of this talk. I also want to mention assertions, which look very similar to the case statements, right? So exactly the same, A or B, but instead of having two circuits, two ways you can go, one fails, right? So this left assertion requires this to be a left value, otherwise it fails. And this right assertion requires this to be a right value, produces an output, or it fails. And this is useful for pruning, which is similar to how in Taproot you can hide everything but successful script power. You can do this in simplicity even further because you can hide everything but the successful if branches. So even in the script itself, you have this pruning, but the way it works exactly is kind of follows through. So happy to answer any questions about it later. Okay, that's it. Those are all combinators of simplicity, not many, and I hope you agree that this wasn't rocket science. Okay. And no mathematical notation whatsoever. Very simple. We can represent arbitrary Boolean circuits, and so Boolean circuit takes finite inputs, a fixed number of inputs, produces a fixed number of outputs. We can do all of them in simplicity, all of them. Finite inputs, finite outputs, like I said, and all functions can be represented. So if there is a Boolean function that takes finite inputs, produces finite outputs, we can do it in simplicity. That's the completeness of simplicity, and I think it's very elegant that with so little we can do so much. And the consequence of that is that we can represent Bitcoin scripts and covenants and much more using simplicity. And interesting is that introspection, right? How can we do introspection into our transaction inputs and outputs? And that we can do using special terms that are called primitives that are basically read-only constants that we can inject into our program. And because of read-only, it's okay. It doesn't do anything. It's not like a side effect that leads to unpredictable behavior. The constant is always the same. And yeah, that's simplicity. One problem is that circuit evaluation is rather slow, or at least it doesn't compare with native C code. And even though our computers are circuits, simplicity and how it's valid is not exactly how computers work. And so one solution to this, to the problem that simplicity is rather slow comparatively, is that you can execute C code, right? So what you can do is you can write a simplicity term. Remember, term is basically a program. You can write C code that can do the same function, because remember, terms are functions from A to B, Boolean functions. We can verify that this C code is actually the same as the simplicity term using this verified toolchain and using verified C and so on. And then what we can do is we can define a jet term, which is just like a constant, like the unit combinator from the beginning. But instead of producing the unit value, instead of producing the witness, it takes the inputs of this C function and produces the output. And this is just as though we had written the entire large term, the entire large program, in one node, in one term. And with that, the simplicity is much faster, and actually in the future, terms/programs will consist mostly of jets. And so we will hide these details that circuits are rather slow and that we have to evaluate each combinator on its own. We will hide that, and we will just use C instead. But it will be verified C. And it will be just as though we had used the slow, but theoretically more pleasing circuit. Right. Let's take a look at that. Let's take a look at one of the smallest examples of simplicity code that do interesting stuff. And this is pay to public key, or pay to taproot the key path spending. So we commit to a public key, and we want a transaction signature for that public key in order to spend the coins. And how we do that is using this program, this simplicity program. There's some notation, but we'll go through it. So public key is given, right? We commit to it, and what we can do, this is described, is we can just hardcode this constant, right? We can represent all functions in simplicity, and so we can also represent a function that takes no inputs and produces just this constant. And so this just produces public key in simplicity as an output. Sighash all, as you might know, produces the hash of all transaction inputs and outputs, also as a constant. And then this is the pair. This is how we write pairs. And so we have the pair of this and this, of the public key, that is hardcoded constant, and of the transaction input and output hash, that is also a constant. And then we add the witness, which the user provides on redemption time when he wants to redeem the coins, when he wants to spend the coins, which is a valid transaction signature for this transaction hash and this public key. And again, this is a pair, so it's a pair, and then it's another pair in one. Three values in one. And this is actually a meaningful symbol. It's not just the end of the line like in C. And so this is the composition, right? So we take this, this basically just produces a constant, right? Public key, sig hash, and transaction signature, and then we pipe that, kind of like, think of it as a pipe, into the Schnorr verification check. And so this checks if this signature matches the public key and this transaction hash. If it works, it produces an output, it produces a unit output, and we can spend a coin. And if the verification fails, then this also fails. And this is kind of like the fail indicator that I talked about. And so either this runs through, produces no output, and we can spend a coin, or somewhere in the middle it fails, and then things are burning. We cannot spend the coins, and we are not happy. And that's it. That's already the program. One thing to notice is that this takes no inputs, right? So this is hard coded. This is also kind of hard coded. Uses transaction hash This is added at redemption time, but it's also technically a constant. No inputs, and this produces also an output. This is the empty tuple as output. And so the way how we write scripts for the blockchain is like that. No inputs, no outputs. Everything is provided as a constant, either at commit time or at redemption time. And if it fails, we cannot spend the coins. If it doesn't fail, if it runs through, we can spend the coins. Right, that's simplicity. Let's talk about Miniscript, right? How does Miniscript and Bitcoin script, how do they relate to simplicity? Let's recap Miniscript and how it relates to Bitcoin script. You might know that there's a Miniscript policy, which is this declarative description of who can spend what. You have a public key, for instance, or you have a time log, and this ends and ors, disjunctions and conjunctions, and those define who can spend the coins. And this you can compile to Bitcoin script, to Bitcoin script representation that has a one-to-one mapping to Bitcoin script. This is one thing you can do. You can also lift it to a semantic representation that enables reasoning about, again, who can spend what, but also how different scripts, how different policies relate to each other, if a policy is subsumed by another policy, and so on. So this is like higher level reasoning. But it's not about committing on the blockchain. One example of this policy is committing to a public key, right? PK of key. And as you can see, there are many ways how this can be realized. So it could be paid a public key hash, with or without witness. It could be paid taproot key, half spending. But here it doesn't matter. These details don't matter. It's all about we commit the public key in any shape or form, and how we realize that in the blockchain doesn't matter to us. And then in the Bitcoin script representation, it does so. We say, okay, we want the key, we don't want the key hash, and then we do checksum on that key alone. So those are the opcodes if you want to compile it to Bitcoin script. Okay, so high-level declarative definition, implementation on the blockchain, and some reasoning. And now simplicity extends that. So the policy is very similar. It's like for Bitcoin script, but instead of compiling to Bitcoin script, we compile to simplicity. We use the same front end, and we replace the backend. And the simplicity representation is a one-to-one mapping to simplicity, but it's much closer to the policy. It's much more natural to compile this policy to simplicity representation, because simplicity's structure matches that of Miniscript, while Bitcoin script doesn't. And in the future, we also want to support covenants and more features in this policy, because we obviously can do more in simplicity than you can do in Bitcoin script. And the semantic representation is also interesting, because what we can do is we can lift the Miniscript semantics to the simplicity semantics. So we have a Miniscript policy. We can compute what its semantics are, and we can have a simplicity policy, and we can also look up and compute what its semantics are. And then we can combine the two. In this way, we can bridge those worlds and compare if simplicity and Bitcoin script actually have the same spending conditions or not. They share the same top level. So maybe there was a lot to put in, to take in, but let me conclude. Simplicity is a better backend for Miniscript. That's one way to describe it. It has sound theoretical foundations, unlike Bitcoin script, and it has high expressivity for future use cases, like governance and other stuff, introspection and so on. It extends the Miniscript ecosystem It has a policy, it has a simplicity representation, it has semantics, and the semantics are shared with Miniscript. And in this way, those worlds are connected. And the APIs in C and Cork, Haskell, and Rust. But it's not just Haskell, it's not just Cork, but you can see is the main implementation. We work with Rust, and Cork is about the theoretical verification and about proving many interesting properties of simplistic programs. Yeah, we hope to deploy it on Liquid soon. Yeah, and thank you for listening. Yeah.
In your description for your talk, you say that simplicity can implement powerful smart contracts because it can express all Boolean functions.
Yeah.
But you use that as a distinguishing point from Bitcoin script. But so can Bitcoin script. Can you name a Boolean function that Bitcoin script cannot express?
Well, the thing is about the term smart contract, right? And covenant and so on, right? To me, those are kind of buzzwords, right? Covenants are, to me, smart contracts that have introspection into the transaction output, right? And they can, by doing so, they can limit the way how you can spend the coins. That simplicity can do, and that Bitcoin script cannot do without the new bits, right? Currently being contested. I guess it depends, right? If Bitcoin script can realize all Boolean functions, usually on the blockchain, like I said, you don't really have any inputs, right? So you just have the witness, right? That's used. You have some constants. That's not really about. You don't really realize implement a calculator, right?
But you can.
But you can, right? So I know. I think there are some output limits, right? So I guess that might limit you. This doesn't exist in simplicity yet, and maybe we will have some limits at some point. But it's interesting insight. So maybe at least when it comes to opcodes, the two are when it comes to Boolean functions, right? Opcodes can do the same. But arguably, simplicity is much more elegant, and currently there are no output limits. Maybe Andrew has something to say.
So in Bitcoin script, you can't add numbers that are larger than 31 bits. You can't multiply numbers. You can't have any strings. So in principle, you could construct any Boolean function by using the Boolean operators in Bitcoin script. But because there's a 201 opcode limit, in practice, it doesn't give you freedom to do a lot of, like, even basic arithmetic. I think it's the most straightforward answer to your question.
Right, so it's good to know that these opcodes have types, right? And 32 bits is the limit by the addition. Whereas in Miniscript, whereas in simplicity, you know, there was no adder, right? We built the adder. We put any adder we want. And then maybe we use jets to make it faster, but we can define any just we want, right? So we can do 128 bits, we can do 1024 bits, doesn't matter.
Have you considered adding the Boolean functions to Miniscript so that you can compile them down to Bitcoin, the equivalent versions in Bitcoin script?
Like, we're working on the way how we can integrate simplicity into Miniscript policies and stuff. I'm not sure if there's any work on extending Miniscript for Bitcoin script. But you are referring to Bitcoin script, right? So
yeah. I guess with elements Miniscript, you have extension plates, right? So you can do that eventually, extending the elements Miniscript with the elements version. I mean, extended version of Miniscript. Maybe you can do that with the extension trait, but in Rust, yes, right? Yeah.
Yeah, so we're not aware of functionality in Bitcoin script today without any further bits, any new opcodes that Miniscript can't. Well, we're not planning to extend Miniscript to add any additional functionality. As far as we're aware, the available extra functionality that you could do with script that you can't do in Miniscript is there are a few like very specific applications. Like one that comes to mind is you can't do weighted thresholds, where you do like a 4 or 5 threshold thing, like that one key counts for 2, say, something like that. You can do that in script, but you can't do it in Miniscript. We aren't planning to add that to Miniscript. I'm just using it as an example, but I could list a bunch of things like that. Mostly because of a lack of demand. Right? I think if people wanted to do that, we would do it, but the trade-off is adding additional complexity to Miniscript itself, right? So you always have to balance that.
So for the implementation of simplicity, like once it eventually comes into Bitcoin, is that it's kind of like taking, like you're no longer writing script at this point, like what's going to be expressed on the blockchain is that when I broadcast my transaction is, if I can look at the script copy, is I'm still expressing using Bitcoin script, but there's like additional opcodes that are introduced with simplicity.
Well, the simplicity would be like a taproot leaf version, right? And
Okay.
and right, new nodes would have to adopt that, right? And otherwise, I guess
So
there would old nodes would just accept that, right?
yeah.
And then execution actually uses a completely different machine. So it uses the so-called bit machine for simplicity that I left out because that's another talk. But basically evaluating circuits, right, on its own, on their own kind of bit machine, and nodes need to upgrade and opt into that, or they just accept this new taproot version.
So it would be a new it would be like a segment version 3 or something, right?
Something like that.
Okay.
And yeah, I realize it's kind of annoying that we have now 2 machines, right? But due to backward compatibility, they cannot provide it.
I had a question about introducing new jets.
Okay.
It seems like you can introduce a new jet sort of with a soft fork, except old unupgraded nodes like won't be able to run it in any reasonable amount of time. So does that mean that every time you introduce a new jet, you sort of have to do a new like script version that the unupgraded nodes ignore?
I mean, we're currently working on a catalog of jets, right, to capture hopefully all major use cases, and that's a huge catalog.
Is the catalog available somewhere?
It's in the tech report, but I'm not sure if it's up to date.
Gotcha.
And I'm working on more learning materials, but I mean, this would work, what you said, right? We can upgrade it to version. I'm not sure. I'm not an expert in consensus, right? So maybe there are ways to do it without it. Yeah.
Because it's just going to be like a new taproot version, right? Is that taproot the value does op success for running on an operator, right? So if you introduce a new jet, then like hey, it's using a new op or whatever it is. So then
I mean, ideally you execute the circuit behind the jet, right?
Okay.
So the jets don't add any new value besides being passed.
Okay.
Right. So it's always some kind of simplicity program.
Yeah.
And it's just compressed. It's just a compression.
Okay.
Right. So it's not a new opcode or anything. Not in the sense that new opcode adds new expressivity. Yeah.
Do you think that you'll sort of be able to create a catalog of jets in the first go that's large enough to sort of capture all the things that people might want to do with simplicity?
Well, I think that's the goal, but I think we need to ask more people what they want. Right? There are lots of arithmetic functions. There's a lot of ECDs A, I even saw. Even though we kind of want to avoid that, we want Schnorr. But there's lots of stuff like the SHA and all that stuff. We cannot guarantee, right, that we can cover all use cases. But deploying a liquid will show us what people want, and then we can work from there.
How do you think about the trade-off between, like you were saying, right? It's like we're doing the ECDSA stuff, but also we want people to use Schnorr instead. So like, what do you think about the trade-off of like just don't implement the ECDSA stuff and then they have to use Schnorr on there?
Like I think this was the idea. So I'm actually surprised myself that ECDSA is even in the catalog. We might drop that. So we might, yeah. So yeah, we want people to use SHA. We want people to use Schnorr, and I think ultimately we'll just disallow everything else. And because it's a new taproot version, it's okay, right? We're done. You can always use the old stuff.
Yeah.
Yeah. So that's that. So I think we will go that route.
But eventually, if the jet is not, compiled or like is not created beforehand, you can still do maybe, eventually something that is not covered by a jet, or,
Yeah.
so you are not limited, like, it's just about,
Jets,
maybe
you can leave
lower.
out, you can just ignore. In theory, you could, like, if you saw a jet node, you could say, okay, I want to execute the entire circuit, I don't want to speed up.
Yeah, okay.
And you can always write anything,
Yeah.
and that might not be covered by a jet. But
But
in most cases, it won't.
won't it just be like, a lot of things will just be like intractably slow, right? Like you'll just never complete, like trying to calculate like a SHA-256 hash in the simplicity bit machine, like would that be fast enough to do it without a jet?
I think we did it, right? But,
Yeah,
but
I
it's
think-
not fast enough.
I think it takes over a minute.
Okay.
Probably does more than 200 operations too.
It would be interesting to kind of compare how much you can do feasibly with simplicity and how much you can do feasibly within Bitcoin script's opcode limit, right? So in this sense, simplicity might actually win, even though the circuits are slowish, right? They're not super slow, but they're not exactly super. I mean, I have a question actually to you guys, like, what kind of learning materials would you like? Who has read the tech report? Or tried, not completed, right? Was too difficult, right? Is there anything that you had in mind or that would help you?
Just more examples. And
More examples?
yeah, like I think that's always like like Barack and the Kara that you guys were this morning, like for all the stuff that you guys have been doing on Nigiri and all those kinds of things, like actual stuff where if I'm like building like a normal web app, like I don't have to go also learn like a simplicity on the side of like, hey, I can just pull this in, plug it into my web app, and like now instead of doing the like descriptors generation that I was normally doing, right? Like I can just plug and play with simplicity, just like examples of like this is how you would do it in Bitcoin script. This is the simplicity, like
Right, like a comparison kind of,
Yeah.
like, I mean,
because there's a lot of like simplicity, not like this is like the equivalent within Bitcoin.
yeah, like this example wasn't in the tech report, for instance, right? And I think this was really helpful. Like for me as well, like I learned more than you guys making this talk. And there are many more examples, right? Like how you can program in simplicity, like approaches to problem solving, how you solve common problems that are solved in Bitcoin script, and how this is done in simplicity. Like good to know. Yeah. We'd also like to see that. Well then, thanks again.